Welcome to our deep dive into the fascinating world of oscillations. In this video, we'll explore the core concepts behind oscillatory motion, simple harmonic motion, and their significance in science and engineering. Oscillations are everywhere, from the swinging of a pendulum to the vibrations in your smartphone. Understanding these rhythmic motions helps us make sense of countless phenomena in our daily lives and in advanced technology. Let's embark on this journey, starting with the basics and gradually building up to more complex ideas like resonance and energy in oscillatory systems. Oscillatory motion refers to any motion that repeats itself in a regular cycle. Think of a child on a swing, a guitar string vibrating, or even the ticking of a clock. In each case, the object moves back and forth about a central position, known as the equilibrium point. This repetitive movement is what we call oscillatory motion. It's a fundamental concept in physics because it forms the basis for understanding waves, sound, and even electrical signals. Let's see how this idea leads us to the concept of simple harmonic motion. Simple harmonic motion, or SHM, is a special type of oscillatory motion where the restoring force acting on the object is directly proportional to its displacement from the equilibrium position and always acts towards that position. Imagine a mass attached to a spring. When you pull it and let go, it moves back and forth in a smooth, predictable way. SHM is characterized by its symmetry and regularity, making it a cornerstone in the study of oscillations. Next, let's derive the mathematical equation that describes SHM. To describe simple harmonic motion mathematically, we start with the restoring force, which is given by F equals kx, where k is a constant and is the displacement. According to Newton's second law, F equals ma, so we set ma equals kx. Rearranging, we get a /mx. This leads to the differential equation d2x/dt2 plus k /mx equals 0. The general solution to this equation is x, t, a cos, omega plus phi, whereas the amplitude, omega, is the angular frequency and phi is the phase constant. This equation captures the essence of SHM. Let's break down three key terms in SHM: amplitude, frequency, and time period. Amplitude is the maximum displacement from the equilibrium position. Frequency is the number of oscillations per second, measured in Hertz, Hc. The time period is the time taken for one complete oscillation. These quantities are interconnected. The frequency is the reciprocal of the time period. Understanding these terms helps us describe and compare different oscillatory systems, whether it's a pendulum or a vibrating string. Time period of simple harmonic motion is a crucial parameter. For a mass spring system, the time period t is given by t equals 2 pi square root m/k, where m is the mass and k is the spring constant. This formula shows that the time period depends on the properties of the system, not on the amplitude of oscillation. The shorter the time period, the faster the oscillations. This relationship is fundamental in designing oscillatory systems in engineering and technology. Phase of oscillation tells us the position and direction of motion of the oscillating object at any given time. It's represented by the angle, omega plus phi, in the SHM equation. The phase helps us compare different oscillators and determine how synchronized they are. For example, two pendulums swinging together have the same phase, while those swinging oppositely are out of phase. Phase is a subtle but powerful concept in understanding complex oscillatory systems. Simple harmonic motion, energy constantly shifts between kinetic and potential forms. When the object passes through the equilibrium position, its kinetic energy is at maximum and potential energy is 0. At the extreme positions, potential energy is maximum and kinetic energy is 0. Despite these changes, the total energy remains constant, assuming there's no energy loss. This interplay of energies is key to understanding how oscillatory systems function and maintain their motion. The kinetic energy, Ke, of an object in SHM is given by Ke equals 1/2 m omega 2, a 2x2, where m is mass, omega is angular frequency, a is amplitude, and is displacement. This equation shows that kinetic energy is highest at the equilibrium position and decreases as the object moves towards the extremes. Understanding kinetic energy in SHM helps us analyze how energy is distributed during oscillations and is essential for solving practical problems in physics and engineering. Potential energy, Pe, in SHM is given by P equals 1/2 m omega 2x2. Here, x is the displacement from the equilibrium position. This means that as the object moves away from the center, its potential energy increases, reaching a maximum at the extreme points. The interplay between kinetic and potential energy ensures that the total energy remains constant, provided there's no damping or external force acting on the system. Total mechanical energy in simple harmonic motion is the sum of kinetic and potential energies. It's given by E equals 1/2 m omega 2 a 2, where A is the amplitude. This value remains constant throughout the motion, as long as there's no energy loss due to friction or other forces. The constancy of total energy is a hallmark of ideal SHM and is crucial for understanding energy conservation in oscillatory systems. Damped oscillation occurs when an oscillating system loses energy over time, usually due to friction or air resistance. As a result, the amplitude of oscillation gradually decreases and the motion eventually stops. Damping is common in real-world systems, such as car suspensions or door closers, where it's important to prevent continuous oscillations. Understanding damping helps engineers design systems that are stable and safe. Forced oscillation happens when an external periodic force is applied to an oscillating system. Unlike free oscillations, where the system moves on its own, forced oscillations are driven by an outside influence. Examples include pushing a child on a swing or the vibrations in a washing machine. Forced oscillations can lead to interesting phenomena, such as resonance, which we'll explore next. Resonance occurs when the frequency of a forced oscillation matches the natural frequency of the system. At this point, the system absorbs energy efficiently, leading to large amplitude oscillations. Resonance can be both beneficial and dangerous. It's harnessed in musical instruments to amplify sound, but it can also cause bridges or buildings to collapse if not properly managed. Understanding resonance is vital in engineering and design. Resonance isn't just a theoretical concept. It appears in many aspects of daily life. For example, when you push a swing at just the right moment, it goes higher and higher. Musical instruments like guitars and violins use resonance to produce rich sounds. Even the shattering of a glass by a singer's voice is a dramatic example of resonance in action. These everyday examples show how resonance shapes our world. Simple pendulum consists of a mass, called the bob, attached to a string, swinging back and forth under the influence of gravity. The motion of a simple pendulum can be described by the equation theta, t, equals theta 0 cos, omega plus phi, where theta is the angular displacement. For small angles, the motion approximates simple harmonic motion, making the pendulum a classic example in physics. The time period of a simple pendulum is given by t equals 2 pi square root L/g, where L is the length of the pendulum and g is the acceleration due to gravity. This formula shows that the time period depends only on the length of the pendulum and gravity, not on the mass or amplitude. This property makes pendulums useful for keeping time in clocks and other devices. Torsional pendulum is a device that oscillates by twisting about its axis, rather than swinging back and forth. It consists of a disc or bar suspended by a wire or rod. When twisted and released, it rotates back and forth due to the restoring torque provided by the wire. Torsional pendulums are used in clocks and scientific instruments to measure rotational motion and properties of materials. Spring mass system is a classic example of SHM. It consists of a mass attached to a spring. When the mass is pulled and released, it oscillates back and forth. The restoring force is provided by the spring, and the motion can be described using the same equations as other SHM systems. This setup is widely used in experiments and demonstrations to illustrate oscillatory motion. For a spring mass system, the time period of oscillation is given by t equals 2 pi square root m/k, where m is the mass and k is the spring constant. This formula is similar to the one for SHM and shows that the time period depends on the mass and the stiffness of the spring. This relationship is crucial in designing mechanical systems that rely on precise timing and oscillatory behavior. Oscillations play a vital role in science and engineering. They are fundamental to the operation of clocks, musical instruments, and even electronic circuits. Engineers use the principles of oscillatory motion to design stable buildings, efficient vehicles, and precise measuring instruments. Understanding oscillations helps us harness their power for technology and innovation. Oscillatory motion isn't limited to man-made systems, it's everywhere in nature. From the rhythmic beating of your heart to the cycles of the moon, oscillations govern many natural processes. Even the vibrations of atoms in a solid are examples of oscillatory motion. Recognizing these patterns helps scientists understand the underlying principles of the universe. Modern technology relies heavily on oscillatory systems. For example, quartz crystals in watches oscillate at precise frequencies to keep accurate time. Electronic circuits use oscillators to generate signals for communication and processing. Without oscillations, much of our technology, from smartphones to satellites, wouldn't function as we know it. Oscillations are closely linked to waves. When oscillatory motion is transmitted through a medium, it creates waves, like sound traveling through air or ripples on water. Understanding oscillations is the first step to mastering the study of waves, which are essential in fields like acoustics, optics, and telecommunications. Engineers must understand oscillations to design safe and efficient structures. For example, buildings and bridges are designed to withstand oscillations caused by wind or earthquakes. Car suspensions use damping to control oscillations for a smooth ride. Mastering oscillatory motion is key to solving real-world engineering challenges. Medical technology also benefits from oscillatory principles. Devices like pacemakers use electrical oscillations to regulate heartbeats. Ultrasound machines rely on sound waves, which are a form of oscillation, to create images of the inside of the body. These applications show how oscillations can improve health and save lives. Communication systems depend on oscillations to transmit information. Radio, television, and mobile phones use electromagnetic waves, which are generated by oscillating electric currents. By tuning these oscillations, we can send and receive signals across vast distances, enabling global connectivity. Music is built on oscillations. When you pluck a guitar string or blow into a flute, you set up vibrations that produce sound waves. The pitch and tone of the sound depend on the frequency and amplitude of these oscillations. Musicians and instrument makers use this knowledge to create beautiful and harmonious sounds. Clocks and watches use oscillatory systems to keep time. Pendulums, balance wheels, and quartz crystals all rely on regular oscillations to measure seconds, minutes, and hours. The precision of these oscillations determines the accuracy of the timekeeping device, making them essential in our daily lives. Electronic devices use oscillators to generate signals for processing and communication. Oscillators create periodic voltage or current changes, which are used in radios, computers, and smartphones. These electronic oscillations are the backbone of modern digital technology. Vehicles experience oscillations in many forms, from the vibrations of the engine to the movement of the suspension system. Engineers design these systems to control and dampen oscillations, ensuring a smooth and safe ride. Understanding oscillatory motion is crucial for automotive safety and comfort. Buildings and bridges are designed to withstand oscillations caused by wind, earthquakes, or traffic. Engineers use damping techniques and flexible materials to absorb energy and prevent structural damage. Understanding oscillations is essential for creating safe and resilient structures. Biological systems also exhibit oscillatory behavior. Heartbeats, brain waves, and circadian rhythms are all examples of natural oscillations. These rhythms are vital for health and survival, and scientists study them to understand how living organisms function and adapt. In chemistry, oscillatory reactions produce periodic changes in concentration, color, or temperature. These chemical oscillations help scientists understand reaction mechanisms and design new materials. Oscillatory behavior is a fascinating area of research in physical chemistry. Astronomers observe oscillations in stars, planets, and galaxies. For example, pulsating stars change brightness in regular cycles, providing clues about their structure and evolution. Oscillatory motion helps scientists study the universe on both small and large scales. Earthquakes, tides, and weather patterns all involve oscillatory motion. Seismologists study the oscillations of the Earth's crust to predict earthquakes, while meteorologists analyze atmospheric oscillations to forecast weather. These natural oscillations impact our environment and daily lives. Light itself is an oscillation of electric and magnetic fields. The frequency and amplitude of these oscillations determine the color and intensity of light. Understanding light as an oscillatory phenomenon is fundamental to optics and modern physics. Sound waves are created by oscillations of air molecules. The frequency of these oscillations determines the pitch of the sound, while the amplitude affects the loudness. Musicians, engineers, and scientists all rely on the principles of sound oscillations in their work. In quantum physics, particles like electrons exhibit oscillatory behavior, such as wave-particle duality and quantum oscillations. These phenomena are at the heart of modern physics and have led to breakthroughs in technology, including lasers and semiconductors. Even economics experiences oscillations, such as business cycles and market fluctuations. Economists study these patterns to predict trends and make informed decisions. Recognizing oscillatory behavior in economics helps manage risk and plan for the future. Psychologists observe oscillatory patterns in human behavior, such as sleep cycles and mood swings. These rhythms influence our well-being and productivity. Understanding psychological oscillations can lead to better mental health strategies and improved quality of life. Artists use oscillatory patterns in music, visual art, and dance to create rhythm and movement. The repetition and variation of forms evoke emotions and capture attention. Oscillations are a source of inspiration and creativity across artistic disciplines. Sports often involve oscillatory motion, from the swinging of a bat to the bouncing of a basketball. Athletes and coaches study these motions to improve performance and prevent injuries. Mastering oscillatory techniques can make the difference between winning and losing. Oscillations are all around us, from the ticking of a clock to the vibrations of a washing machine. Recognizing these patterns helps us appreciate the science behind everyday phenomena and the role oscillations play in making our world function smoothly. Summary: oscillations are a fundamental aspect of both nature and technology. From simple pendulums to complex electronic circuits, understanding oscillatory motion unlocks a deeper appreciation for the world around us. Whether you're a student, engineer, or simply curious, mastering the principles of oscillations opens doors to innovation and discovery. Thanks for joining us on this journey through the science of oscillations.